Hi all, today we are going to study the topic vector diagram of transformer for different loads. This is a very important topic. So far we have studied the concept of ideal transformer, but before learning the vector diagram of transformer under different load conditions, we have to do a step-by-step approach to understand the concept of actual transformer from ideal transformer. As a first step of it, we will consider the transformer with winding resistance alone. So far we have considered ideal transformer. In the case of ideal transformer, we didn't consider the winding resistance as ideal transformer was a lossless one. Now we are considering the case of transformer with winding resistance alone. The winding resistance in primary is indicated as R1 and the winding resistance in secondary is indicated as R2. Definitely due to this winding resistance, there will occur a voltage drop in both these windings. We will see that in detail later. For the convenience of calculation, it's better to transfer the winding resistance of both windings either to primary side or to secondary side. That is, either you can transfer this R2 resistance also to the primary side, or else you can transfer this R1 resistance to the secondary side. Whenever we are making this transfer, it must be ensured that the effect remains the same. That is, when this resistance R2 is in the secondary side, it causes the copper loss I2 square R2. If you are transferring this R2 resistance to the primary side, then also this same loss must occur. This resistance R2 when transferred to primary side is indicated as R2 dash. So the circuit seems to be like this. The resistance which were present at the secondary side has been transferred to the primary side, and now it is indicated as R2 dash. Now we have to find the relation between this R2 dash and R2. While this resistance was at the secondary side, the copper loss which occurred there was I2 square R2. As I told before, when this resistance is being transferred to the primary side, that is R2 dash, it must be ensured that the same copper loss will occur at primary side also. As you know, the current which is flowing through this primary side is indicated as I1. So when this current is flowing through this R2 dash resistance, the copper loss which is occurring in it is indicated as I1 square R2 dash. Its value must be same as that of I2 square R2. It is represented here. I1 square R2 dash value must be same as that of I2 square R2. From here we will be able to obtain the relation between R2 dash and R2. That is, R2 dash can be written as I2 by I1 the whole square into R2. I2 by I1 is actually the inverse transformation ratio, that is 1 by K. Therefore we can write R2 dash is equal to R2 by K square. This is how we have transferred the resistance at the secondary side to the primary side. When we are transferring the resistance from secondary side to the primary side, we will be indicating it as R2 dash. And the relation between R2 dash and R2 is R2 dash is equal to R2 by K square. This is actually R2 by K square. So now the effective resistance at the primary side is indicated as R01. It is actually the sum of R1 and R2 dash. Similarly, it's possible to transfer the resistance at the primary side to the secondary side. When we are transferring the resistance at primary side to the secondary side, we will indicate this resistance as R1 dash. The current which is flowing through the secondary side is I2. Therefore, the value of I2 square R1 dash is same as that of I1 square R1. From there, we will be able to obtain the relation between R1 dash and R1. That is actually R1 dash is equal to K square R1. That relation is obtained in the same manner. Now the equivalent resistance at the secondary side is indicated as R02, and R02 is actually the sum of R2 and R1 dash. You must know these transformations without any confusions, then only you will be able to solve the problems related with equivalent circuit. Till now we have considered the transformer with winding resistance alone. But in actual transformer, in addition to the winding resistance, there exists a leakage reactance. In order to understand its concept, we will consider a transformer with leakage reactance alone. For understanding this, let's see the concept of leakage flux first. A transformer core with primary winding and secondary winding is shown here. If you see in this transformer diagram, a very small portion of the flux won't be linking with both the windings. Such portion of the flux is called as leakage flux. Here you will be able to see when current is flowing through the primary winding, definitely a small portion of the flux, which is indicated by this red lines, are not linking with the secondary winding. Similarly, when current is flowing through the secondary winding, a very small portion of the flux is not linking with the primary winding. So this small amount of flux is said to be the leakage flux. The nature of this flux is also alternating in nature. As this flux, that is this leakage flux, is alternating in nature, when it is linking with both these windings, definitely it will cause an EMF to get induced in both these windings. According to the Lenz's law, that is, the direction of induced EMF is such as to oppose the cause that produces it. If you try applying it here, you will be able to see that the EMF which is getting induced in both these windings due to the leakage flux will be opposing the ultimate cause of this leakage flux, which is actually the supply voltage. As the EMF induced due to the leakage flux is opposing the supply voltage in accordance with the Lenz's law, their effect can be, that is the effect of this leakage flux, can be indicated by a reactance in the concerned winding. It is clearly indicated here, and this reactance is said to be the leakage reactance. The reactance in the primary side is represented as X1 and the reactance in the secondary side is X2. Once again I am telling you, while considering the leakage reactance of transformer here, we haven't taken the resistance into consideration. That is, the winding resistance is not taken into consideration here. Unlike ideal transformer, actual transformer will be having both this winding resistance and leakage reactance. Therefore, the practical transformer can be indicated like this. In the primary side, there exist both the winding resistance and the leakage reactance. Similarly, in the secondary side also there exist both the winding resistance and leakage reactance. Primary side impedance is indicated as Z1 and the secondary side impedance is indicated as Z2. When we considered the ideal transformer, this R1, X1, R2, X2 were not there. So the supply voltage V1 was same as that of the induced EMF in the primary side, that was E1. Similarly, E2 was same as that of V2. But now the case is different. Now the supply voltage V1 is not same as that of E1. Whenever current is flowing through this resistance and reactance, definitely there occurs a resistance drop and reactance drop, and the voltage which you are getting over here will be the difference between the supply voltage and the drops which are occurring in this resistance and reactance. Therefore, we can write the relation for V1 as V1 is equal to E1 plus I1 into R1 plus JX1, or else we can write it as V1 minus I1 R1 minus J into I1 X1 is equal to E1. This R1 plus J into X1 can be indicated as the impedance term Z1. Similarly, the EMF which is getting induced in the secondary is represented as E2. You will not be getting the same value at this terminals. When you are connecting a load across this, definitely there will be occurring a drop in both this X2 and R2. So the voltage which you are getting across this load will be E2 minus I2 R2 minus J into I2 X2 is equal to V2. Or else you can write it as E2 is equal to V2 plus I2 into Z2. Now the concept of ideal transformer and practical transformer is very clear for you. Next we are going to consider the vector diagrams of this transformer when different types of loads are being connected here. Different types of loads means you can either connect a resistive load here, or else you can connect an inductive load, or else you can connect a capacitive load. When all these three different types of loads are connected, their corresponding vector diagrams are analyzed in detail. All of you must learn to draw these diagrams. That is this vector diagrams. This is a very important one. You don't need to by heart it, you just need to follow the steps which I am going to say. Then you will be able to draw it by yourself. First we will consider the case when the load is a resistive one. That is the load which is being connected across this terminals will be a resistive load. So in that case the vector diagram seems to be like this. So let's see the step-by-step instructions to draw this vector diagram. Here I have shown it as 10 steps. It's very easy one. Just listen very carefully. As we have already seen the transformer on no loads vector diagram here, this line will be indicating the direction of flux, and the induced EMFs are shown here E1, E2, and this is supply voltage and I0 current is also indicated here. Also I can say you have seen this vector diagram. This will be indicating the direction of flux, and the direction of induced EMFs are E1, E2, which will be lagging the flux by 90 degrees. I have explained it very clearly in the last session. So in the first step, we will be drawing that same flux line, and E1, E2 will be actually in this direction. But we will consider this bottom portion as the secondary part and this top portion as the primary part. Hence we will transfer the E1 from here to the top portion. That's why we are indicating it here as minus E1. So this is indicating the no load current, that is I0. In step 2, you have to draw V2. V2 is actually the voltage which is appearing across the load in the secondary side. You have to draw this V2 lagging E2 by some angle. The voltage appearing across this terminal is actually V2, and the load which is being connected here is resistive load now. Since the load which is connected here is resistive load, definitely the current which is flowing through the load I2 and the voltage which is appearing across this load V2, both will be in phase with each other. Therefore in step 3 we will be drawing I2. This is actually I2. I2 starts from here and it's till here, and it is in phase with V2. It is drawn in phase with V2. From this relation it's very clear that E2 can be obtained by adding V2 plus I2 R2 plus J into I2 X2. So in order to obtain the value of E2, first we will be adding I2 R2 with V2. The value of R2 is usually small value, so definitely the value of I2 R2 will be also a small one. So if you are seeing here, at the tip of V2 we are adding I2 R2, which is shown as a blue line here. This is step 4. In the step 5 we have to add I2 X2 with V2 and I2 R2. Already we have obtained V2, then this is I2 R2. So this line from here till here will be indicating V2 plus I2 R2. You have studied the concept of RL circuit in your basic electrical engineering course in your first year. There you have studied the impedance triangle and all. The same concept is being used here also. So in order to draw the line for I2 X2, you have to draw a line perpendicular to I2 R2. That is, you have to draw a line perpendicular to I2 R2 at the tip of I2 R2. That will be indicating the term I2 X2. So now this is V2, this is I2 R2, this is I2 X2. If you are adding these three terms, V2 plus I2 R2 plus I2 X2, definitely you will be getting E2. The secondary side is over. Now we have to move to the primary side. Before that we will take a small glance at this equivalent circuit of transformer. This is actually the secondary part, and this is actually the primary part. This I0 is actually representing the no load current, and the primary current is I1, which is being taken from the supply, and this portion represents I2 dash. If I0 were negligible and if we haven't taken this into consideration, then definitely the value of I1 and I2 dash would have been same. But if you are taking this I0 into consideration, then definitely the value of I1 will be the vector sum of I0 and I2 dash. This I2 dash is actually the primary equivalent of secondary current, which is I2. So in the next step we will be just extending this I2 line to the primary side also, and its length will be quite smaller than I2, because this value of I2 dash will be definitely smaller than that of I2, as I2 dash is equal to KI2. Now we know I2 dash and I0. By using parallelogram law of addition, we will be able to do the vector sum of these two vectors, that is I0 and I2 dash. From here we will be able to get the value of I1, that is by using the parallelogram law of addition. We have find the value of I1 because I1 is actually the vector sum of I0 and I2 dash. Now if you see in this relation, you will be able to obtain the value of V1 by adding E1 with I1 R1 and J I1 X1. So with this E1 term, we will be adding I1 R1. To draw this line, you have to draw a line parallel to I1. Okay, I1 R1 will be always parallel with the line I1. So while drawing a line parallel with I1 with a small magnitude, because the value of R1 is very small, which is less than 1, therefore this will be indicating I1 R1. So E1 plus I1 R1. Next we have to obtain J I1 X1. In order to obtain I1 X1 drop, you have to draw a line perpendicular to I1 R1 drop like this. This will be giving you I1 X1. So now you know E1 plus I1 R1 plus J I1 X1. This J itself indicates that I1 X1 is perpendicular to I1 R1. So E1 plus I1 R1 plus J I1 X1 will be giving you the value of V1. So the vector sum of E1 plus I1 R1 plus J I1 X1 is shown here as V1. All of you must take a paper now itself and follow the steps and try to draw the diagram by yourself. Then only you will be able to do it for your exam also. You have to practice drawing this 2 or 3 times to get a thorough understanding of this topic. Next we are going to consider an inductive load being connected here. Inductive load means it's not actually a pure inductor, it will be an RL load. Only if we say it as a pure inductor, we can say that the current which is flowing through the load and the voltage across the load, both will be having a phase difference of 90 degrees. But if we are considering an inductive load means RL load. In the case of an RL load, definitely the current which is flowing through the load will be lagging the voltage V2. V2 is the voltage which is appearing across the load by some angle theta which is lying between 0 and 90. You have studied about it in your basic electrical engineering course. That's the concept of RL load. So while drawing this vector diagram, when the load is inductive, the first step you have to draw I0, E2 minus E1. Then lagging E2 you have to draw V2. Only difference is in this case the I2 won't be in the same phase as that of V2 because the load which we have connected is inductive one. So definitely I2 will be lagging V2 by some angle phi 2. This is how you have to draw I2. And then while drawing I2 R2, you have to draw a line parallel to I2 with a very small magnitude at the tip of V2. Please listen carefully. You have to draw a line parallel to I2 at the tip of V2 that will be indicating the I2 R2. In order to draw the I2 X2, you have to draw a line perpendicular to I2 R2. So this will be indicating I2 X2. So now you know V2 plus I2 R2 plus I2 X2 will be giving the value E2. In the next step, you have to extend this I2 towards the primary side, and this will be indicating as I2 dash, which can be represented as KI2. I0 plus I2 dash will be giving you the value I1. Now at the tip of E1, you have to draw a line parallel to I1. That will be indicating I1 R1 with very smaller magnitude, as the value of R1 is very small. Then you have to draw a line perpendicular to I1 R1, which is actually I1 X1. So now E1 plus I1 R1 plus I1 X1 will be giving you the value V1. In this if you are seeing in this diagram, this I1 R1 I1 X1, its resultant is also shown here. This is actually representing a small impedance triangle. So this will be definitely I1 Z1. Similarly here I2 R2, this is I2 X2. So definitely its resultant will be I2 into Z2. Considering case 3, the load which is being connected here is actually a capacitive load. If the load which is connected here is a capacitive load 1, then definitely the current which is flowing through this load will be leading this terminal voltage V2 by some angle. Capacitive load means it's not a pure capacitor one, it will be RC load. If it was a pure capacitor one, then definitely this current I2 would have lead V2 by 90 degrees. Since the load which we have connected here is an RC one, so definitely this I2 will be leading V2 by some angle which is lying between 0 and, just like we have drawn I0, E1, E2. In the case of resistive load and inductive load, the same thing can be drawn here also. So first we will be drawing this line, then E2, then E1, then this will be representing I0, and this is actually V2. Since the load which we are connected here is actually a capacitive one, so definitely the current which will be flowing through the load will be leading the voltage. So we have marked I2 here leading the V2 by some angle. So now in order to get the value of E2, you have to add I2R2 and I2X2 with V2. So to draw the line of I2R2, you have to draw a line parallel to I2 with a very small magnitude, because the value of R2 is very much less than 1. So definitely you have to draw a line parallel with I2 at the tip of V2. This will be indicating I2R2, and then you have to draw a line perpendicular to I2R2, that will be indicating the I2X2 term. So if you are seeing here at the secondary side, you will be able to see this is V2 plus I2R2 plus I2X2, and this I2R2 plus I2X2 is represented here as I2Z2. So directly we can say V2 plus I2Z2 is equal to E2. Now moving to the primary side, you have to just transform this current I2, you have to just extend it. That line is not represented here, but in actual practice you must extend this line towards the back side, and that will be indicating I2 dash. Then at the tip of I0, you have to draw a line parallel to this I2 dash, and then by using the parallelogram law of addition, you will be able to get the value of I1. As this is indicating E1, in order to get V1, you have to add I1R1 and I1X1 along with E1. So for obtaining the line of the vector of I1R1, you have to draw a line parallel to I1 at the tip of E1. So this will be representing I1R1, and this will be representing I1X1, and this is actually I1Z1. So E1 plus I1Z1 or E1 plus I1R1 plus I1X1 will be giving you the value of V1. So this is how we can obtain the vector diagram of transformer under capacitive load. You must learn to draw all these 3 vector diagrams. These are very important ones. So in today's session we have studied very clearly the concept of actual transformer. What are the distinguishing features between an ideal transformer and an actual transformer? Comparing with the ideal transformer, we will be taking the resistance parameter and leakage parameter also, leakage reactance parameter also into consideration in the case of actual transformer, that is the practical transformer. Thereafter we have learned the vector diagrams of transformer under resistive load, inductive load and capacitive load. With that, we are completing today's session. Thank you.